for me is to talk about as if somebody's standing and looking at a car go by. So let's say this car is going by at 30 meters per second. Okay? To you, if you're standing there watching that car, it's going 30 meters per second. How fast is that car going relative to the driver in the car?
Zero.
Zero, right? Because he's moving with the car. So relative to you, it's moving at 30 meters per second. Relative to the person in the car, he's not moving at all. Fair enough? So if I was asking you how fast you were swimming in a river, that's kind of the question we're going to look at. So you're going across the river. If in still water, I asked you how fast you were swimming, you would say whatever the speed was. So you're swimming at 2.4 meters per second, let's say. So that's how fast you're actually swimming. But if there's a current in the river, then you're now swimming at the rate that you swim at, plus or minus the rate at which the current is carrying you. Fair enough? So relative to the riverbank, for example, you might be swimming in a straight line this way. The river might be moving you that way. So to me, standing there watching you swim, you're going like this, even though you're doing your best to swim in a straight line. But relative to me, you're going this way. Relative to the water, you're just going in a straight line. But you don't know that the water is actually moving you as well. So what we want to look at is basically, how do I tie that all in? How do I find out, based on the direction or the current of the river, how fast do I swim, and so on. So here's the question. It says a swimmer can swim at a speed of 1.8 meters per second in still water. If the current in the river, at 200 meters wide, is 1 meters per second to the east, and the swimmer starts on the south bank and swims so that she's always headed directly across the river to the north, determine each of the following. All right. Basically, turn your textbook over for a second like this. This is a question that is best if we don't read it out. We look at it and we talk about it. Okay? So I have a swimmer that, if there was no current that day, would swim directly across the river at a constant speed of 1.8 meters per second. Okay? Now the river is 200 meters wide. So the first thing I'd like you to do, just before we get into a discussion about this, the first thing I'd like you to do is calculate how long is it going to take that person to get across the river. So going at a constant speed, this is 200 meters. What is it?
111.11 seconds.
11 seconds. So it's going to take 111.11 seconds to get across the river. Everybody knows, take the distance divided by the time. That makes most amount of sense, right? Okay. Well, the question says that then, though, that the current is moving in this direction now. Again, because we learned yesterday that I add vectors together by drawing tip to tail, right? It's moving at this speed of, what was the speed of the current? 1 meter per second, I believe.
Oh, and times it by the time.
And it was to the east. Okay, so far? Now, I want you to think this through for a second. What is the shortest amount of time it's going to take for that swimmer to get across the river? 111.11 seconds, right? As if there was no current, that's the fastest they could possibly swim going across the river. However, what if you were swimming with the current, though? Would you get across the river faster?
No, because you'd be traveling a farther distance.
Yeah, exactly. Exactly correct. All right? I would be swimming faster, correct? But I would be swimming further, more on that line. So to the person standing down here watching you do what you got to do, you're moving like this across that river, right? the shortest possible distance is straight across. You're going to move faster, but you're also going to go at a greater distance. So the first thing I want you to do then is tell me, would the time change?
Yes.
Would you be swimming longer or shorter if you're swimming with the current going across the river?
You want to say?
I do the same amount of time.
Same amount of time, you think so?
Yeah.
I think it'll be close to the same amount. I don't think it'll be exact. It'll be like
I
within
think,
5
I
seconds.
How
think,
come?
Because you're going faster, like, but it's a bigger distance.
Mhm.
A big distance, but you're still swimming faster than you were if you're just going straight.
I think it's going to take longer because you're going faster, but not towards the other side. You're just going sideways faster, which doesn't affect anything, except that you're going to be swimming farther at your same velocity, which is going to take more time to cover. Like you're swimming, your speed is higher, but you're not going in the right direction with that speed. It's causing you to go in a farther direction. This is going to take you longer to cover that distance.
Okay, let me put it a different way then. All right? He says pretty much the same. He says it's going to take you longer. What happens if I want to actually swim straight across? I want to end up straight across. So what direction do I have to swim?
Upstream.
Northwest.
Say it again.
Upstream.
Upstream, okay. What does that mean? Swimming into the current, right? I'd have to swim into the current in order to end up straight across from where I started. You would all agree?
Yeah.
So it would look something like this. I'm going to make a mess of my board, but I'd have to swim somewhere up there, right? In order to end up right there. You all agree?
Yeah.
Okay. Would it take me longer or shorter or the same amount of time to swim upstream and end up straight across?
Well, I think it would take you longer if you had started out
Well,
there.
you just told me it takes you longer going the other way.
Well, it does because the triangle expands.
Well, it could be
No,
close to
but
the
the-
same again.
If you swim that way, the current's pushing you as you're swimming.
I know, but you're going out that, like, you'd be like going like a loop-de-loop, right?
Loop-de-loop.
It'll be like the same.
No,
I know,
you-
I've done
My question to you is this then,
that.
all right? We all got great ideas right now. Relative to the water, does it change how fast that person swims?
No, the person will stay the same. They can't get stronger than they already are.
Perfect. Great. So that's the first correct answer we've had so far. All right? Everybody else, we're kind of conflicted, but you'd all agree with her that the speed that that swimmer swims at relative to the water would still stay the same. I can only swim as fast as I can swim. Agreed?
Yeah.
So that 1.8 meters per second wouldn't change, would it? Okay? But relative to the shoreline, can I swim faster or slower? Is that a possibility? Relative to me standing on the shoreline watching you swim?
Yeah.
Yeah. Think about it. If you're running with the wind or running against the wind, if you're swimming into the current or swimming with the current, is there going to be a difference?
Yeah.
Yes.
Sure there would be, right? You're going to swim faster if you're with the current. You're going to run faster if you're with the wind than you would into the current or against it, right? Okay, so let's figure this out then. All right? I'm going to tell you that Rowan was right. It's going to take the same amount of time for me to go across swimming with the current as if there was no current. That time remains the same. Okay? So that time then would be 111.11 seconds. Now I'm not going to end up across from where I started, am I?
No.
How far downstream am I going to end up?
111 meters.
How do you get that?
I times the velocity of the current times the time.
Right. So I'm going to end up 111.11 meters downstream from where I was actually intending on ending up. Do you agree?
Yeah.
All right, let's use Pythagoras' theorem for a second here, and let's do a little math. Let's find, first of all, the joint velocity, the speed at which I swim at, which is 1.8. The speed at which the current is pushing me, which is 1. Let's find out what that combined speed is.
No, you have to go 1.8 squared plus 1 squared.
Right.
Oh, yeah.
Because if it was directly behind me, then you're right. I would just add those together, but it's affecting me on an angle, right? Okay, so what is it? 1.8 squared plus 1 squared, which is? And the square root of it? Go ahead. Alexander.
Well, the answer is 1.8.
It's what?
The answer is 1.8. It would be 3.24.
Well, because the 1 squared is,
Go ahead, say this again.
Okay, 1.8 squared plus 1 squared.
Yeah.
Is 3.24, and then the square root of that is 1.
Give
No,
No.
2.05.
2.25 times.
it should work out to 1.8 because 1 squared is useless.
No, it's not
No,
useless.
it's 1.
Oh, yeah, I did it wrong.
1 squared is 2,
1 squared.
1 squared is
or
1.
sorry, 1,
One.
right? But you're still adding it on to 1.8 squared. So it's still going to have a minuscule effect. What did you guys say it was? 2 point what?
2.059.
2.059. So it's got quite a bit of an effect on it. Because this is small as well. Right. So the combined swimmer and current speed is 2.059 meters per second, right? We all get that? So if the current was acting directly behind that person, I would just simply add 1 and 1.8 together. Right? But it's not. Okay, let's do the same thing now, and let's find out our distance.
Something like that, part of that.
So I want from here to here.
Oh, 220.79.
Would you get 200 and...
28.791.
Perfect. Thanks, Ron. 228.791 meters. 200 squared plus 111.11 squared, square root it, I get 228.791 meters, yes.
So the current makes up for the extra distance
This
you
way,
cover.
this way. I want to explain everything to you. The explanations come. I just want to make sure my numbers are right before I do this. We okay? You sure? Because you got to prove me right here. With that distance and that speed, how long does it take to get across?
111.12 seconds.
111.126 seconds.
Same thing.
Same thing that we got to begin with.
And is the distance over velocity?
All right?
Excuse me for the interruption. Lane Warmer to room 9, please. Lane Warmer, return to room 9.
You're going to swim faster. You're going to swim further. But the amount of time it takes for you to get across doesn't change that. Okay?
What about the other way?
I'm going to get to that right here. The biggest thing is what I want you to see right here. The number one thing I want you to take from it. The shortest period of time for you to get across the river. You're going to see these questions a couple times. The shortest period of time for you to get across the river is as if there's no current. So just simply take the distance over the speed that you can swim at. And that's the shortest amount of time you can get there. Because even though you can swim faster, you can't swim faster in the straight line. It's going to take you further, and it's going to take you the same amount of time. Okay? Are we okay so far? So what do we learn? Relative to this guy, this person going straight across, or this guy going on an angle, it's going to take the same amount of time for them to get to the other side of the river. They won't be where he wants to be. He'll be down the river, right?
Mhm.
So far, so good? Questions?
The 1.8 and like that's just a straight line in the middle of the triangle. Like
Yes.
this? And
Yes.
then the other one's the
I'll-
one on
The green one I'll talk about.
but
it
the
later.
red one is for the one above on the right.
Correct. Yeah, so he's
That's-
swimming across, the current's moving him this way, this is
Okay.
that's the, oh man, can't even think of the word right now. So that's the speed, that's the combined speed of that and that. Okay? So far so good?
Yeah.
All right, now, let's look at this the other way. As if I want to go straight across. I want to end up over here. So we all agreed this velocity right here is 1.8 meters per second, right? Oh, sorry, kibosh that. Okay. I want to end, excuse me, I want to end up straight across. Now this is important for you to grasp the logic behind this. If you want to end up somewhere, okay, because we're going to do plane questions right away, airplane questions, in which an airplane wants to end up in a certain spot. So in order to end up in a certain spot, you have to go into the current, up the stream, or you have to fly into the wind and let the wind blow you back if you want to end up where you're supposed to. Agreed?
Yeah.
Okay, so I want to end up right here. But in order to do that, I have to take into account that there's this guy right here, this current, right? And then I'm going to have to swim up here. We all agree? Okay, I'm going to show you something. Again, every year I seem to change the way I teach this thing. I'm going to show you something that I haven't done before either. All right? So I'm going to call it ground, or no, yeah, that's fine. Ground speed, let's say. I'll talk about ground speed with airplanes. So the ground speed is if you're looking up at the airplane and you're watching it go and you're finding out the distance and the time and you can see it, that's the ground speed. So that includes the wind and the speed of the actual plane. Well here, my ground speed is going to be the swimmer plus the current. Okay? Don't write this down. Just watch. So my ground speed is the speed at which the swimmer is going plus the speed of the current. So far, so good? Okay. Now, the swimmer is going in this direction right here. We know the velocity of the swimmer, don't we? 1.8. And then I know that my current is 1 meters per second. So this would be to the north, this would be to the east, right? Okay? But the problem is, okay, I may have messed this up, but I'll see if I can save this. I gotta find, how do I get this so it's subtract? Velocity of the swimmer. I want to know what the speed of the swimmer is. The speed of the swimmer would be the velocity of the ground minus the velocity of the current. Okay, so far? Agreed? Okay, so, it's maybe a colossal failure, but I'm going to try anyways. So, the velocity of the ground is going to be, the velocity of the swimmer is this right here. But I have to go this way first.
So what if you started over?
And over to here.
Would that work?
Let's ignore this. I messed this up. I'm going to come back to this. I thought I could make it make sense to what I taught you yesterday, but it's not going to work quite as easily. All right, so let me just finish by explaining it. I'll finish with what I started. This is actually the swimmer. This is the way the swimmer's got to go, right? So what do we say the swimmer's speed is?
1.8.
1.8 meters per second, like that. Agreed? Okay. The current's going at 1 meter per second that way. So how fast is the swimmer actually moving now? Is he going faster, slower, or the same speed as what he was doing?
Slower.
If you're going into the current, you're actually going slower, aren't you? And what is the actual speed?
1.497.
How do you find that?
The square root of 1.8 squared subtract 1 squared.
Pythagoras' theorem says I have this squared plus this squared equals that squared, correct? So to find this guy out, I take this squared, subtract that squared. Because this is my hypotenuse. Right? How far across the river is it?
Same distance, 200 meters.
200 meters. What's the time it takes to get into there?
111. No?
1.33.
What did you get?
1.33 or 133.63 seconds. I get 600 or 601. The time 123 601.
Oh, 601?
Yeah.
You said for this?
Yeah.
So you took 200 divided by 1.497?
Yeah, I got.
Try that again.
I didn't do 1.49, so I didn't round it off.
Oh, okay.
Yeah.
Okay, so what is this right here, guys?
601.
601 seconds. So 133.601 seconds. Did it take them longer to go across or shorter? Longer. Does it make sense that it should take them longer?
Yes.
Yeah,
He's swimming
because he's swimming into the current.
Swimming into the current.
like directly
The current's slowing down.
into the
You gotta fight against it.
The other way
Yeah,
is
you
somewhat.
Yeah, but
with
so
the
then,
current.
so when you're swimming with the current, then you should be quicker.
Yes,
Yes.
but you're going
You
further.
weren't.
That's the
Oh,
same
we're
thing.
quicker.
It's the same speed.
2.059 meters per second.
Sorry, I mean with like less
The
time.
time's not right on that one either.
What do you mean with less time?
But you're going farther.
You're going further.
Awesome, because the time going straight across is 111 seconds. So if you're going like straight across and against the current a little bit, so you're going to be slower.
What if you wanted to end up at that spot, but you just started over a bit? That would take you to, right?
And then you're doing this.
It's a different spot.
So you're walking across and then swimming across. The whole point is to start at that spot and get across from where you're looking. So in order to do that, you have to swim into the current to do that. Okay, now, there is one other aspect of this that we do want to know, okay? And that is, I want to know what angle, okay, and this is the tricky part, what angle relative to the bank do I have to swim in order to end up across from where I started? So the first thing I want you to do is I want you to find that angle right there. So where is 1 in relative to the B?
Opposite.
Where is 1.8 relative to the B? So which trig function am I talking?
Sun.
Sine. So I go sine B is equal to 1 over 1.8. B is equal to 749. Thank you. Okay? So that's the angle right here. But if it asks you, which it does in the book, it asks you to find it relative to the bank. So how do I put that in as relative to the bank?
You flip, subtract it from 90.
Right. So what would that be?
56 and 251,000.
Relative to the bank. Okay? Again, not only a difficult question in terms of the math because we just used Pythagoras' theorem again. And we just used one trigonometric function. That's all we did to solve this question. But the understanding of the question is the part that confuses us. What are they looking for? So now let's flip back to our book and let's answer the questions that were asked. In A, the swimmer's resultant velocity, that's the word I was looking for and I couldn't think of, and it was an R word. The swimmer's resultant velocity relative to the river bank. What is the resultant velocity in this case? In A?
.059.
2.059 meters per second. That's this guy right here. Remember, I was swimming with the current, right? So that's A. B says, how long will it take for her to reach the far shore? How long did it take to reach the far shore? 111.11 seconds. Okay?
Where's the far shore? Like, I know it's right across, but it doesn't matter which corner they're talking about, or?
Just the others.
Just from the time it takes you to go from here to the other side. Okay? And when you're calculating that, you don't use the current for it. Because that time and that time are going to be the same thing. Right? And then C says, how far downstream will she land from the point opposite her starting point? So how far downstream did she end up? 111.11 meters. There's A, B, and C. So nowhere in that question do you see all of this. This is added on. But the next question that you work with in the book deals with this. Okay? How are we doing? This is an introduction to vectors. Very, very quick introduction into it. Vectors can cause a lot of grief, but they can be a lot of fun too when you create these questions. All right? But again, it's just trigonometry. And you have done trig since grade 9. You did a pile of it in grade 10. You're doing lots of it now. You can do lots more of it in grade 11 and 12. So here's why we started applied this year with trigonometry, was for this section. Okay? Any questions about what I just taught you today? All right, that's all I've got for you today then. Okay? I assigned 3 questions to you yesterday. Page 93.
Did we do them already or no?
I drew them for you, yeah. And I kind of set them up for you. Page 97, questions 2, 3, and 4. And then there's 5 questions on page 102. And that's it. You've got 40, 50 minutes today to do all that. All right? Of those of you that started yesterday's questions, were you okay on drawing out number 3? Did we try it or didn't get a chance?
I couldn't get it.
You couldn't draw it
I got confused.
on number 3?
On what page again?
93.
Yeah, I got confused. I didn't know, like, I drew it out, but I didn't know where to go from there.
You did a great job. But here's the thing.
Yeah.
Okay, so you did awesome. That's exactly how it looks. Okay, so if you look at this, you go 10 to the northeast. That's that. You go 5 to the west and 2 to the south. And then you've got that right there. So the green represents my displacement, right? Okay, so now I have to determine how to solve it. Now, this is why, again, you could figure out triangles and you could draw out triangles and find it. It's hard to do, right? But what if I did this? What if I said, okay, let's scratch this for a second. Let's just simply draw out, and I would suggest this for any time you have 3 plus vectors, okay? Draw out each individual vector on its own and then find out what the 2 components are for each vector. So in the 10 kilometer, or is it kilometers?
Yeah.
I think so, right? So here's 10 km, northeast, which makes that 45 degrees. Do you agree? Yeah? So there's an east component to it and a north component to it, right? So let's find out how much east it is and how much north it is. Okay? Then what I'm going to do is I've got 5 kilometers west. Well, there's only one component for that. It's only horizontal, so it's 5 kilometers west. Right? And then I have 2 kilometers to the south. Like that, right? You follow me so far?
Yeah.
Okay. So there's only one component to this guy as well. So I'm going to put this and this together and this together on a chart. and redraw it so that I can get a triangle that's simply a right triangle. So what do I know so far? I know this is 5 kilometers to the west. That's one of them. I know this is 2 kilometers to the south. So what do I have to find? I have to find out what the east component here is and the north component is right here. So how would you do that?
Will they be the same?
Yes?
Um,
You don't know how to do that?
I cannot.
Okay. I want to find out the measure of this side right here.
Right trig.
Oh, yeah, there we go. Right trig.
Right? So where is this in relation to that?
Opposite,
And that?
hypotenuse,
Which trig?
sine.
Sine 45 times 10 gives you that.
Yeah.
Right?
Yeah.
Then that goes right here.
Oh, yeah.
And then same thing, same amount,
Yeah.
that goes right here. Then you draw your line, add and subtract these, because these are going north and east, and these are west and south, right? And then draw a right triangle at the end, and that the hypotenuse of your right triangle is the length of line that you were looking for to begin with.
Okay. Yeah. That
Okay?
makes sense.
Is that better?
Yeah.
All right? So yeah, when I draw components, I'm only using right angle trig at that point.
Yeah.
Okay? Anybody else?
So then you take the nets, like you
Yeah.
draw your line and then you take the nets and that's your height and base.
Yes.
Pretty sure you know the triangle, right?
And so when I did this and this and this right here, right? My new triangle will be that right there. What do you think? Really, John said I'll leave it there. Okay? So basically what I'm doing is finding this right here. That's exactly what I'm finding. Do you see that test? I'm actually finding this triangle to help me solve it.
Yeah.
And that's what it's going to look like over there when I draw it out. Okay? Anything else today? Okay. Move through a few of those just about.
Doesn't have 9.
Yep.
Can I get a 1, please?